Long arms. Sorry.
Hey everyone. So Silette has asked me to make this video to kind of show how the tutorial will work. And because we're all here right now, I have roped in my family to help. Thanks. So, in this scenario, which the groups will be doing on their tables and playing out, I am Bob, Annie is Eve, and Mum is
Karen.
Karen is Alice. Yeah. So, these boxes represent encryption. If a message is in the box, then it can't be viewed by Alice even as she passes it along. Eve, even as she passes it along. Thank you. And these locks are different forms of encryption. You kind of can't see the small one. Here's a bigger one. These locks and the keys, the lock is a public key and the key is a private key. They are a pair and the private key unencrypts the public key. They will be labeled in the tutorials, and they will be bigger than this one. It's just the ones that I had available. So, the first super simple RSA key exchange starts with Alice advertising her RSA public key. So Alice passes the public key, to Eve, who passes it to Bob. Bob then encrypts a message. Just pretend that I put a message in here. Encrypts a message back to Alice using the public key. There we go. This makes it unreadable to others using encryption. And so Bob passes it back to Eve, who passes it to Alice. Alice can then use her private key, which she hasn't shared with anyone, to unlock the box and to read the encrypted message. Woo! So, what's the attack? We, in our tutorials, will ask the student groups to figure out what the attack is. And so that's the questions that Shannon wrote for last year or earlier. Assuming that the RSA algorithm is secure, how can Eve use her powers to read or alter the message? And so once they figure that out, the solution is reasonably simple. Alice, we'll just take out the private key. Alice passes, and I'll take my box back. Alice passes her public key to Eve, but Eve replaces it with her own public key and passes that on to Bob. Now Bob has no idea that this has happened, and so Bob goes, okay, I'm just gonna lock up this message using Alice's public key, which is totally normal. Passes it back to Eve, but Eve can unlock it, have a look inside, and then relock it with the other, with Alice's key, and pass it back to Alice. Yeah. And so Alice unlocks it, thinking, oh yeah, it's encrypted with my public key, so nothing could have gone wrong. Surely this has come directly from Bob. But because it was unencrypted in the middle there, evil Eve, could do whatever she liked with it. Nice. And just to kind of show that it works, even though neither of these two have pretty much any experience with cryptography, Annie was figuring out the attack as I was explaining it ahead of time. Too smart.
All computer science can be explained by envelopes.
Yeah, pretty much.
That is what I have learned.
Yeah. So that's the first simple RSA exchange. A faster protocol is the RSA exchange to exchange a secret key. So these locks are the secret key encryption. Both parties encrypt and decrypt using the same secret key. And the way that you change the key on these locks is you unlock it, currently at 00, and turn it to 90 degrees. You push it down quite hard. There we go. And then you can change the number. So I've just changed it to 01. You let it go, and then it locks on 01 instead of 00, or 0000. Let me just reset that. Cool. So, the RSA to exchange a key. A fast protocol goes like this. Alice advertises her RSA public key. Yep, and passes it over to Bob. Thanks. Bob generates a secret key K for the secret key secret key encryption algorithm like AES. So I'm going to write down the secret key for this combo lock, and Annie will definitely never figure it out. Cool.
Eve. Additionally.
Eve. Who's Annie? Yeah. Alter ego.
That's the word.
That's the one. Bob encrypts Bob encrypts the normal message using the secret key algorithm. So in the group, they change the lock to the secret key. And then wait, I've done yeah. And then passes it via Eve to Alice. And now I just realized that I've done this the wrong way. Now, Bob encrypts the key for that box using Alice's public key. And then sends this, oh, there we go, sends this back to Alice. So Alice decrypts that message to find out the secret key, the shared secret. Eve has no idea, of course. And then nice. And then can unlock the actual message. Yay! Wow. So, what's the attack on this one? I'll take the stuff back. The attack, thank you. I'll need that one in this box as well. Yes. The attack is pretty much the same as last time, and so I'm hoping they'll get it pretty quick. Alice advertises her public key and passes it by Eve, but Eve is sneaky and passes on a different public key, not her private key. You'll need that term. And so Bob goes, great, I know the public key for Alice. And so Bob encrypts the secret key using that public key. And passes that back. But now Eve also knows the secret combination. Eve knows the shared secret. And so Eve re-encrypts it and passes it back. And so now, when Alice and Bob encrypt their message using the shared secret, Eve also knows the shared secret. And so this is a failure of future secrecy. Because Eve, all Eve has to do is just take a copy of any message, and then she can decrypt it, read it, do what she likes, or manipulate it in the middle. There you go. Thanks. So, yep. Which brings us to Protocol 3, and this is the trickier one. The Diffie-Hellman key exchange. So, Bob and Alice agree on public values G and P. And so Alice picks some small ones.
Numbers?
Small numbers, G and P. Yeah, just
two
pick
small
some
numbers.
Yeah. Normally they would be big. Which one's which? Yeah, cool. Normally they would be big, but for today's purposes they will be small. And so Alice sends that to Bob.
Mm-hmm.
Eve also learns the numbers in the middle. Yeah. We can get rid of that. Then Alice generates a secret number A and does G to the A mod P. Do you need to know what G is again? So pick a small
Yeah, you
A.
do that.
Yep, cool. Eve doesn't. Yep.
Okay, no. I don't know what mod means, but never mind.
Fair. Yeah. So
They know what mod.
they should, but we may have to explain it.
Mm-hmm.
It's a good thing to know. And so Alice passes only the calculated value to Bob. Nice. Now, Bob, thanks, also picks a B. And so Bob writes down the secret value G to the B mod P. Mod is just the remainder after you divide by that thing.
Mm-hmm.
And so I'm going to write, for reference, Mum did 2 to the 3 mod 7. And so I'm going to do... Alice did 2 to the 3 mod 7.
We know what's going on.
Yeah.
We got this.
I'm going to do 2 to the 4 mod 7. Which is 16 mod 7. Which is 2. Yeah. And so Bob passes back to Alice that value of 2. And Bob has a value of 6 over here. Now, Alice and Bob both put that number to the power of their chosen number, their chosen A.
Mm-hmm.
So you, you chose 3,
mm-hmm.
and so you do it to the 3. And I chose 4, so I do mine to the 4. That's a big number. 6 to the 4 is 1296.
Did you do that right?
Divided by 7. So you did 2 to the 3 is 8.
Yes. Yeah. Okay.
Yeah.
How?
Yeah.
Very different numbers.
Well, yeah, they get very big very quickly. And so my remainder is 1. Yeah. And so, because it's mod, we have the same remainder again.
Right.
So the remainder of yours, mod 7,
Is 1.
is 1, and the remainder of mine is also 1. Well,
Okay.
and so because we have the same remainder, even though we never said our powers publicly, we have figured out the same secret number. But Eve doesn't know.
Eve does not know what's going on.
Eve does not know what's going
does not
on.
know what's going on.
And Eve doesn't know the secret number. And so we can then encrypt a message using, was it this one? Yeah, this is the one I changed. Using that number. And so, Bob, pass it back by Eve to Alice,
Who also knows the number.
who also knows the same secret number and can unlock. Nice and easy, cool. Nice and easy. And so that is the Diffie-Hellman key exchange. Yeah.
Excellent.
Excellent. Now, hopefully they should have experience with this one from the lectures, but you will need to devote more time to this one just because it's slower to play out than the previous ones. I would say even devote half an hour just to Diffie-Hellman and the attack. So, the attack on Diffie-Hellman.
Oh, gosh.
This is the last one. Yep. The attack on Diffie-Hellman is that Eve intercepts the messages and replaces them with her own numbers. So let's play that out.
All right, from the top, everybody.
From the top. So I'll just put those over there. Alice and Bob agree on public values G and P. These are the same ones. These can just be the same as last time, and it doesn't matter if Eve uses the same ones as well. So there you go. Yep. Alice generates a secret A. How many pieces of paper? Yeah, and does A equals G to the capital A equals G to the A mod P. So the same thing as before. Pick a small power. It can be the same small power as before if you want.
Mm-hmm.
Yeah. Cool. And so does. Yeah. And so for this one, Alice has picked 4 to be lowercase a. So it's 2 to the 4 mod 7. Which is 2. Yeah. Now that gets passed to Eve, and Eve goes, neat. I'm going to replace it.
The A.
Yeah. And so
3.
Eve picks her, yeah.
There you go.
Instead of 2 to the 4 mod 7, Eve goes, I'm going to pick a different number. And so it's 2 to the 3 mod 7. And so Eve passes that one on to Bob instead. Yeah. Cool. Now Bob goes, okay, cool. I'm going to do mine. And so I'm going to do 5. So I go 2 to the 5 mod 7, which is 32 mod 7. Which is, it's 0.57 times 7. Let's find out. 4. Nice. That's 4. And that is 1. And so Bob passes that back to Eve, who then replaces it with another one in the opposite direction.
Oh gosh.
Yeah.
Yep.
This is why this one's complicated.
A equals. So
You can do the same, like you did 2 to the 3 to me, you can do 2 to the 3 with Mum if you want.
okay, it's the same mod.
Yeah, same one. Cool.
Won't that mean you have the same number? If I give you the same thing, and then you know the secret.
Oh yeah, no, that is true. Okay, do 6.
Okay, I know things.
You do know things.
No, 2 to the 6.
2 to the 6.
Okay, I don't know things.
Yeah. And so 2 to the 6 mod 7 is 1. Yeah. And so now,
But this is the same number.
yes, it wouldn't be if the numbers were bigger.
Will they get that?
Hopefully.
Okay.
Yeah.
Sorry.
Yeah, I may have to disallow certain numbers. I'll have to do that maths.
Oh no. That's just my reaction. So I have to do that math.
Yeah. Doing maths.
Sorry.
Anyway,
Yep.
so now each of us can do our this number to our normal power. So Alice does that number to the power that she picked, which was 4.
So 1 to the power of 4.
1 to the power of 4. Yeah, nice.
Oh no.
And then Bob does 1 to the power of, what did I pick? 5, which is 1.
So you was.
So even in trying to avoid it, we hit it anyway. And we now have the same shared secret. We shouldn't. We should have a different shared secret to you two's shared secret, but yeah,
Right.
we do. I'll iron out the maths, and I think I'll have a slide of these are the numbers you can pick. Anyway.
Yes. Yeah.
And so Eve in the middle figures out the this was mine. So figures out 4 to the 3 mod 7, and we'll get the same as me, which is 1. And then over here 2 what was this?
4.
Yeah, cool. To the 6 mod 7, and we'll get again 1. We should have different numbers. We don't in this case, but we should. And I'm not going to re-record this so that we do. You can deal with it. You can figure it out. So,
We'll do maths.
yeah. Bob encrypts the message using the shared secret. And so changes the lock to the shared secret and encrypts the message using that number. Ooh. There we go. And passes that to Eve. Now Eve can decrypt it. No, the other one. There we go. Eve can decrypt it using our shared secret, the Bob and Eve shared secret, and then re-encrypt it with the other lock, which is the same number in this case, but would normally be different.
That's not the right number. I'm locking it. What?
Yeah, only locks and unlocks if it's on the right number. Re-encrypts it and passes it on to Alice, who decrypts it. And so because Eve has effectively made an extra secret key, and so now there's 2 secret keys, one for us 2, one for them 2, instead of 1 secret key between Bob and Alice. Eve can intercept all communications and just keep switching out the locks as they go. That's Diffie-Hellman. And so that is all of the tutorial. I'm hoping that it being physical will make it easier for the students to understand. We'll see how we go. One last thing. Before we let the students out, get the students to reset all locks to 0000. The way that you can check that they've been reset is check that it's 0000, and then check that it opens and closes, because it will only lock and unlock if it's on the code. Thank you very much.
Ooh, yeah. Okay, that makes sense.